Okay, in this video we're gonna extrapolate a little bit more about the fundamental theorem of algebra. And before we talked about the fundamental theorem of a polynomial or of a polynomial of degree x. So we have all these other terms, but we care about the degree x, where that is the degree, the degree n. The degree n will equal or determine the number of zeros in our polynomial. However, this will be this can be expanded upon a little bit, because remember, our zeros, our total number of zeros, can be broken down into several different categories. We can have real zeros. We can have free zeros, like an example of x equals to 4 or x equals to -1/2. Those are real zeros. We could also have irrational. So a type of, let's actually say imaginary. So let's say imaginary here. Imaginary. We could have imaginary values like 3 plus I. And we're going to learn that if 3 plus I is an imaginary zero, then 3 minus I must also be a zero in that same polynomial. And then within our real category, we can have irrational zeros. So irrational zeros, and that could be like 3 plus square root of 2. And we're going to learn that if 3 plus square root of 2 is a irrational zero, then 3 minus square root of 2 is also going to be an irrational zero. So for right now, let's go ahead and focus upon this video. Let's talk about these irrational zeros, and how they come about. So let's go ahead and say that we have an example here. So let's say we have an example. And in our example, we are going to say that we have f of x is our polynomial, and he'll be equal to x squared plus 4x minus 6. And I ask you to determine the zeros, or the also known as the x-intercepts, also known as the solutions, also known as the roots. So all four of those are the exact same word. They are synonyms of the exact same word. They're all values that we know the function will cross the x-axis. So in this circumstance, if we want to find the zeros, we say, can this factor rapidly? Can't factor, because I don't know any factors of negative 6. I don't know any factors of negative 6 that add together to be positive 4. So what do I recommend using? I recommend using the quadratic equation. So the quadratic equation is going to be negative b plus or minus, this is going to be x, equals to negative b plus or minus the square root of b squared minus 4ac all over our value of 2a. And that's going to be the quadratic, well, actually, I shouldn't say equation, I should say formula. So this is the quadratic formula. I shouldn't really say equation. Those are all equations. Equations have equal signs, but formulas are the ways that we can calculate the roots or the x-intercepts or the solutions. So let's go ahead and identify our a value, our b value, and our c value. So our a value is going to be the value of the leading coefficient, because remember, a quadratic equation, this is where it would be correctly termed, is ax squared plus bx plus c equals to a function. So our a is our leading coefficient. That's going to be a value of 1. Our b is the coefficient preceding the x, which is going to be a value of positive 4. And my c is just my constant. And here my constant is going to be a value of negative 6. So now I know my a, my b, and my c, so we can go ahead and plug on in. So we're going to have x equals to negative b, but b is a value of 4, plus or minus square root of b squared, which is going to be that value of 4 squared, and I'm going to extend my square root sign, minus 4 times a, but a is 1, times c, but c is negative 6, all over a value of 2 times a, but a is equal to 1. So we will have x, we're going to simplify this, we're going to have x equals to negative 4 plus or minus the square root of 4 squared is 16, negative 4 times 1 times negative 6 is going to be positive 24, all over a value of 2. This will give me negative 4 plus or minus, that's a plus or minus, there we go, plus or minus the square root of 16 plus 24, that's going to be a value of 40, all over a value of 2. And this will equal to negative 4 plus or minus the square root of 4 times the square root of 10, all over 2. And that's going to equal to, I'm simplifying continuously, negative 4 plus or minus 2 root 10 all over 2. So I can go ahead and I can factor out a value of 2, or I'll factor out a value of 2. So I'll be left with 2 times the quantity of negative 2 plus or minus root 10 all over a value of 2. And now my 2's will cancel. Woo! And I have negative 2 plus or minus root 10. So I'm going to have one zero, or one intercept, at negative 2 plus root 10. And notice I have another 0 at negative 2 minus root 10. Notice with our quadratic equation, a quadratic formula, based off the formula, we have a plus or minus. So unless this b squared minus 4ac, which we're going to later term the discriminant, unless that equals to 0, we're always going to have 2 solutions. So if this is a positive value, underneath that radical, then we know that we're going to have 2 real solutions, 2 real zeros, but they're going to be irrational because they have a value underneath the radical that cannot be simplified. That square root of 10 cannot be broken down into a perfect square. Or it is not a perfect square. Not that it can't be necessarily broken down into one, but it's not a perfect square. So we have 2 real solutions that are irrational. So this brings up the specific quality that if a plus b root c is a 0 of a polynomial, then we call it conjugate. Conjugate a minus b root c is a 0 as well, not a polynomial, is a 0 as well. So irrational zeros must always occur in pairs. Irrational zeros must always, and I like to emphasize these words that are absolutes, like always and never, and always and never are the most common ones you see in math. Always and never are the most common ones you see in math. Irrational zeros must always occur in pairs. So let's go ahead and examine. Let's just go ask some questions now, since we know irrational zeros must also always occur in pairs. So if we had a cubic term, so let's say we had f of x equals to some cubic term and a cubic polynomial, do we recognize that this can intersect here, and then it can continue down and then bounce back up like such? So notice here we only have one place where this crosses the x-axis. So here we know we're going to have one real 0. Okay, so what does this imply? This implies our next video topic, that we know that since we have a degree of 3, that we recognize that we're missing 2 zeros, and it just so happens that with our one real 0, we're also going to have 2 imaginary zeros. So in our next video, we're going to talk about our imaginary zeros.